22, yeah.
Okay. So there's I have an invited talk by Bob Kowalski on combining logic and rules-based programming. And then there's 4 smaller talks plus a break. So I guess, and Michael Kiefer is the chair for the invited talk. So I guess I will pass the floor to Michael and he will introduce Bob. Right?
Thank you. Can you hear me?
Yes.
Thank you. So it's my pleasure to invite Bob Kowalski, who is a legend in logic programming and doesn't really need introduction. So today his talk is going to be about his new language. Well, it's not exactly new, but maybe 5 years old, which combines declarative and procedural features. So I suggest that if somebody has questions, you raise hand on Zoom, and then at the end of the talk, I will let a few people ask the questions, and hopefully everyone will be able to ask questions. Okay, Bob, please.
Okay.
The floor is yours.
Thank you very much, and it's a great honor to be asked to join you today. And let me see, do you see my screen?
Yes.
Yes.
Okay, so let me have a start. Then, slideshow. Okay, so my talk is about combining logic programs with imperative programs. And the proposal I'll put to you is a language called logic-based production systems, which I've worked on with the colleagues you see also on this slide. Now, not everyone I've worked with will agree with my slogan that LPS is a more human-oriented form of computing, but that's really more up to you to decide than to me or the people I'm working with directly. So let me start by motivating this language and then talk a little bit about what it looks like. And if I have time, and I'll work very hard to stick to my time, we may be able to look at some examples running online. So LPS is not only a programming language. It's as much and even more, maybe, a database language, and even more than that, a knowledge representation language, as well as a candidate for a model of human thinking. And if that sounds extreme, I will try to justify that extreme claim. But I will also be addressing more practical problems. In particular, what is the relationship between logic-based approaches using logic programming in particular and imperative state transition systems, ordinary imperative programming, which is the dominant approach to computing today. And in particular, when you look beneath the hood, as it were, and you look at what distinguishes these two kinds of systems, I think you'll see that there are basically two kinds of rules. There are the logic programming rules that some of us know and love, and then there are other kinds of rules, which are more like condition action rules or reactive rules. And do these two kinds of rules have some kind of relationship, and can they live with one another, and can they actually benefit one another? So if what I'm about to propose sounds crazy, then I'm not the only crazy one, because in the world of cognitive science, there have been people such as the Nobel Prize winner Herbert Simon and his colleagues who've argued that there are computational models of human thinking, which are both good models of the way humans think, but also practical from the point of view of implementing computer programs. And they've advocated, for example, the use of production systems as both languages for implementing computer programs, but also for understanding the way humans think. There's a competitor these days, which is logic programs as a model of human thinking. And this book by Stenning and Van Lammauchen shows how the non-monotonic nature of logic programs makes it very suitable as a model of certain kinds of human thinking, at least. And in particular, they look at the famous or maybe infamous Wason selection task, which is perhaps the most widely studied psychological experiment concerning human reasoning. And they show that if you interpret conditional expressions or rules, as we would sometimes call them, if you interpret them as logic programs, then that can explain why what seems like irrational or illogical reasoning for a human actually begins to make common sense. But in the world of hardcore computing, we also have these two kinds of systems or two kinds of rules. David Harel, for example, points out that there are two kinds of computer systems, one of which might be called transformational systems, and they include functional programs and logical programs. And he regards these as the easier kind of computer system to analyze and to understand. But he has the opinion with which I have to confess I've also come to slowly agree, that the reactive systems associated with production systems, for example, are not only the more difficult case, but the more important case. So logic programs, I will argue, are important and they fulfill a very useful function, but that function is subordinate to the function that we obtain when we look at reactive systems in particular. Now, this distinction between different kinds of systems has been noticed not only in cognitive science, not only in programming languages, but also in database systems. So we have two kinds of database systems. We have deductive database systems, which are basically logic programs of a certain kind, and we have active database systems. And these active rule database systems are basically production rules of the kind that I mentioned to you a moment ago. This distinction between two kinds of rules with different kinds of behavior and different kinds of functions has been drawn attention to in many different fields. I've extracted from a paper about normative systems. Normative systems include legal systems, for example, and rules and regulations as you find them in social contexts. And they notice, and it's a big topic in this field, that there are two kinds of norms: regulative norms, which regulate human and social behavior, and constitutive norms, which abstract from raw experience and conceptualize it in more abstract terms. And these, I would maintain, are more like the kinds of rules we find in logic programs, whereas the regulative rules, which regulate human and social behavior, are much closer to reactive rules. In the field of business rules, we have a similar distinction. There's an approach called the semantics of business rules and vocabularies, where they use a modal logic, which has two main modalities. One modality is used for giving guidance, rules that people follow, regulative rules, in other words, and structural rules, which are about meaning, they say, but meaning in the sense that they give abstract characterizations of hierarchies of concepts, like views in relational databases. Stenning and Van Lammauchen call it the great divide, or the big divide, the divide between descriptive rules as of the kind that we find in logic programs and what they regard as deontic conditionals, which I would rather see as something closer to production rules in production systems. So that's good. We have two kinds of rules, but are these two kinds of rules competitors, or are they different sides of the same coin, or how do they interact and support one another, if at all. Well, in the book I wrote 11 years ago, I argued that an intelligent agent, whether it be a real or artificial agent, needs to have both beliefs about the world and goals for how it wants the world to be. And that distinction between goals and beliefs, which are at the heart of what it means to be human, are also a guide to how production system rules and logic rules can interact and complement and find their place in a more intelligent view of not only computing, but also human, what it means to be human. This distinction, which is so important, is often overlooked. Mathematicians or school teachers, when they teach children algebra, they're very free, very often, to write equations such as x equals 2x plus 2. This is the equality, by the way, of mathematics, not the equality of assignment statement. And they're very free to write other kinds of equations, such as x plus y equals, oops, x plus y, I meant to write y plus x. But you see, there's a big difference between these two equations, a difference which ordinary mathematics does not make clear. The first equation is a goal, and the second one is a belief. It's a goal because you want to solve the equation to find out what is the value of x, whereas the second equation is a belief, because we believe that for all x and y, x plus y equals either y plus x, which is what I intended to write, or x plus y, which is what I did write. Either way, it is a belief. So the distinction between goals and beliefs is fundamental to human affairs. It's something which is difficult to understand, and it's something that mathematicians do not draw attention to, even when it's fundamental to teaching high school algebra. So LPS combines logic programs, which represent an agent's beliefs, and it combines them with reactive rules, which represent an agent's goals. In addition to reactive rules, we have constraints of various kinds, and this combination actually is related to Mark Denneker's combination of first-order logic and logic programs, or inductive definitions, as he sometimes prefers to call them. In addition, LPS embeds beliefs as logic programs and goals as reactive rules and constraints. It embeds them in a changing world, which generates observations of external events, inputs, if you prefer to think in more computing-oriented terms, but which can in turn be changed by actions that the agent performs. Outputs, again, if you prefer to think in computing-oriented terms. In addition to changing the external environment, the agent can use models of the external environment, that is to say, internal representation, which we would, in LPS, represent as sets of facts, which change with time and which can be modified as a result of both external events and the agent's own actively generated actions. So what is computation in LPS? Computation in LPS attempts to satisfy its goals, which have the form if antecedent, then consequent, which is a generalization of production rules, as well as constraints, which we write in the form false if conditions. So computation in LPS is goal satisfaction. And it's mainly, it's more closely related to imperative notions of programming than it is to logic programming. A model, which LPS attempts to generate, is a possibly infinite sequence of destructively updated states and state transitions generated incrementally in time, starting from an initial state, external events change that state. LPS models those changes internally in a similar fashion to the way the external world destructively changes its state. So these models are what LPS these models are what LPS generates with the intention of making its goals true. LPS is a helper, sorry, not LPS, logic programs are subordinate, they help the imperative component, they help the agent to achieve its goals. They are the beliefs that the agent has, which hopefully are true in the world. They have the form of conclusions, if conditions, and they evaluate the antecedents of reactive rules to determine whether they are true. And when they are true, they generate actions to make the consequence true. So they help the reactive rules to change the world to satisfy its goals. You can picture it like this. You have an unending cycle, never-ending cycles, and you can start anywhere you want. Let's say you start with the current state. You're in some current state, and you have updates, which result from observing external events and your own actions. And then you determine whether any reactive rules antecedents have been made true. You use logic programs to reduce goals to sub-goals, both to evaluate the truth of the antecedents of reactive rules, as well as to reduce the consequence of the reactive rules to sub-goals, and ultimately either to facts that are true currently or to actions that can be performed in the future to make those consequences true. You then have to choose. You have to decide when there are several alternative options, you need to decide what to do. And having made such a decision, you need to assimilate your decisions together with any external events, having performed those chosen actions, and the world goes round. The world goes round and round, whether you're a human agent or whether you're an artificial agent. This is the way thinking with goals and beliefs looks like in a system such as LPS. So we have an implementation of LPS, which with luck I'll be able to show you. You'll have to tell me how I'm doing for time, because I don't want to contribute to this problems that we're having with timing, and I'm more than happy to stick to my time.
Yeah, you have 22 minutes left, so there's
Okay,
plenty of time.
Thank you, Michael. So I'm showing you screenshots, and these are here both partly for the record and partly in case my demos don't work because of one thing or another. So in LPS, we have to declare our fluents, which are those facts which change with time. And here's a very simple example, which many other authors have used to illustrate their system. So the light can be either on or off. A light can be either on or off, and we can have an event of switching the light switch, and the effect of the switching event will either be to turn the light on if it was off, or turn it off if it was on. Now, this event of switching can also be an action. Some external events can only take place externally, whereas some, as in this case, can be actions and which are disjoint from external events, but in this case are a subset of external events. On line 7, you have a reactive rule. If the light is off, then switch. And of course, what you expect and what you want is that the next state, and here we are dealing with models of the world which are state transition systems. In the next state, if the light was off, then the light will become on. I say next state, but actually I lie. I'll explain what I mean in a moment. We also have a logic programming rule. So to distinguish between them, we write reactive rules in this forward direction, which is the direction in which we run them. First, we evaluate the antecedent, and then we make the consequent true. But in the case of logic programming rules, we also write them in the order in which we run them, because we run them backwards to evaluate whether and when a light is off. So for example, to evaluate the antecedent, we reduce the problem of determining whether the light is off to the subproblem of showing that the light is not on. Where here not is actually classical negation evaluated in the current state. So we have a logic programming rule used as a belief in order to evaluate whether or not the light is off. And here on lines 11 and 12, we have a little causal theory, which tells us how the world changes in response to both external events and actions. In particular, the switch event or action makes the light on if the light is off, and it stops the light from being on if the light is on. Let's imagine that the light is on initially, namely in the at time 1. So these times are really more like states. They have durations, and events take place in the transition from one state to the next. So this is a very simple model of time, but it's one which is adequate for our purposes. So initially we have an example where the light is on, and we observe an event which is external, that the light switch has been switched between state 1, let's call it, and state 2, and similarly has been switched between state 3 and 4. But we have this reactive rule which says whenever the light is off, which is the case at time or state 2, because it's been switched off between times 1 and 2, whenever the light is off, which you see here, then the light will be switched, and the result of switching the light will be to make the light go on. So if we continue, we will have these other external event, the light goes off, and the reactive rule will make the light go on. So when we write an LPS in this sugared up syntax, if light off, then light switch, what we really mean is that for all times at which the light is off, it means if the light is off at any time, then there will be a time in the future or immediately that we switch the light so that it becomes on implicitly. So this reactive rule does not explicitly state the obvious implicit goal that you want the light to be on, but rather it's the goal of what you should do. It's a rule that regulates the behavior of the model of the agent's actions in this case. In the case of the logic programming rule, light off if not light on, this is shorthand for saying that the light is off at any time t, if it is not the case that the light is on at t. In other words, it's in the same state. This is a view on the extensional fluence. So only light on is stored as an explicit fact. The fact that a light is off is an emergent property, so to speak, a ramification, you might say, of the light not being on. And similarly for the sentences that the switch initiates the light on if it's off, the switch terminates the light on if it's on. These are shorthand for rules which say that if you switch the light on, if the light is, let's say, if the light is off at a time t, then switching the light will make the light on at the next time. And similarly, if you switch the light and the light is on, then it terminates the light. But to understand why we write and why we interpret the initiates and terminates sentences in this manner, you have to understand the underlying logic of the state transitions, which I'll come to in a moment on the next slide. But initially, light on is shorthand for saying the light is on at time 1, and observing that switch event from 1 to 2 means that it happens in this instantaneous transition from state 1 or time with duration, time period 1 to time period 2, and similarly 3 and 4. In order, what you need to know is these meanings are embedded in a causal theory like the event calculus or situation calculus, which describes how facts, what facts are true. So if an event happens in the transition from one time to the next, and that event initiates a fluent, then that fluent will be true in the next state. And similarly, if a fact holds at a time t, and no event happens to terminate the event in the transition from t to t plus 1, then the fluent will go to the next state. This sentence is sometimes called a frame axiom, and logic-based systems typically use such frame axioms to reason explicitly that if a fact holds in a given state or at a given time, and nothing happens to terminate that fact, then the fact will be true in the next state. And this kind of frame axiom has been a challenge in artificial intelligence knowledge representation, but a challenge not only for knowledge representation, but also for the computational overhead of reasoning and copying the facts that are true from one state to the next by an explicit computational procedure. It's important to note that in LPS and similarly in all imperative languages, computation is never performed by reasoning in this manner. Computation is always performed by means of destructive updates. And this can be justified if we think of computation as model generation, because computation as model generation allows us to generate models using destructive updates. So if you look at a typical example, one which was inspired, Michael, by your work in transaction logic to a large extent, we can define transactions as taking place over time, starting, let's say, from one time t1 to another time t2, which consists of a sequence of flashing lights, starting from the light being off, and then a flash of light, which lasts for 2 units of time and is separated by 1 unit of time. I won't take the time to explain this to you, but I'll show you what it looks like in practice. Tell me how I'm doing for time, please. Am I coping? I think I'm maybe going to be okay.
You still have 12 minutes, so you have time.
Okay, great. So here let's try running this. So here we've got some observations which are in this timeline, and we can use the definition of this transaction. So here we have a transaction that takes place from time t1 to t4, consisting of a sequence of flashes. So given these observations, which you see here, we can have a reactive rule which says if you evaluate the definition of SOS and determine that an SOS has occurred, then perform the action of shouting. And when we run the reactive rule, we get this behavior here. On the other hand, if we replace this reactive rule by the reactive rule, if true, then SOS, and if we comment out the observations, then what we obtain is not a recognition that there has been an SOS, but rather we generate the sequence of action which creates the SOS. So these, you could think of this as a plan on how to generate an SOS. But the same plan can be used to recognize the complex event, so to speak, of an SOS having been observed. Look at this. We have a reactive rule now which says if there is an SOS from up to a time t, let's say, then generate an SOS from 3 units of time later. So if we're given, for example, a sequence of switches of light which can be recognized as an SOS, then the system, the agent, let's say, the agent will generate an SOS, and having generated an SOS, will recognize that there has been a new SOS, and it will generate another SOS. Maybe this was not what we intended, but this is what we wrote when we said our goal is to generate an SOS whenever we see one. Another nice feature of LPS is that we can generate animations by displaying one state at a time. And I think I'm going to, I'd rather show you this online rather than spend much time on it. Now, if we generalize the notion of switching to have 3 arguments, switching, who is the agent who is doing the switching, what is the current state, just to make it easier to write the program, and where is the agent located, then we can write rules, reactive rules, such as if Bob is in a place at a time and light is off at the time, then Bob switches the light in that place from off to on from the next time, which is the time at which the light is actually off. So this means, of course, that whenever Bob is in a place where the light is off, Bob will immediately switch the light on. On the other hand, Dad doesn't like lights being on. They especially when energy is so expensive. If light is on in a place and Dad is at the place, then Dad is going to switch the light off in that place immediately. On the other hand, Dad has extrasensory perception abilities. If the light is on anywhere, at any place, and Dad's not at that place, Dad knows that the light is on, and he's going to go to that place. But he's not necessarily going to go immediately because because there may be many lights on at many places, so we will not specify the time, and that the semantics of that is one I can explain else at another occasion. We can write these animations in declarative sublanguage of Prolog, simply showing how the fluents, in this case, location and light, how to display them. So the fluent for location is displayed if we're the location of a person, an agent. So we just need to declare what kind of shape is used for the person P, where that shape is located, how big that shape. Here I've chosen a very simple representation of an ellipse, and both Dad and Bob are painted green, as you'll see if and when I manage to give the demo. So when we run the demo, you see an initial state where Bob is in the living room, Dad's in the kitchen, the light is on. Dad shuts the light off, has to make a decision which room to go to, because the light is, so he decides to go to the bedroom. And what's he going to do? He's going to shut the light off, and then he'll go to either the living room or to the bathroom, and that's a decision he'll have to make. So if we now look, I'm going to summarize before spending a few minutes showing you a demo, if all goes well. So for me, the logic-based semantics of LPS is absolutely essential. It's essential because it's used not only for modeling computation, but it's also used for modeling human thinking, goals, and beliefs. So the models that an LPS agent can generate are not arbitrary models, but they're models that are constrained by what the agent believes and by the actions that the agent can perform. And these in turn are minimal models of the stratified logic programs that constitute the agent's beliefs. So logic programming plays an important role in restricting the kinds of models that the agent can construct. The agent also needs a kind of decision theory to choose which actions to execute to make its reactive rules true. And its reactive rules are goals which are guaranteed to be satisfied because they are explicit goals that are driving the agent's behavior, and they need no proof to show that they are true. However, other goals, which can be expressed in arbitrary first-order logic, may be satisfied implicitly. For example, if the light is off at time t, then the light will be on at time t+1, is an emergent property of the simpler reactive rule, which has as its consequent that the switch takes place between times t and t+1. Notice that input and output have a pure and maybe even beautiful logical semantics without needing the complexities of category theory. That logical semantics is simply as sentences which are part of the minimal model that constitutes the agent's beliefs. I should mention that we are also working on a natural language version of both Prolog and LPS, which allows us to exploit the very close relationship between human thinking and human language and transport and embed that into a computational context. What will programming look like 50 years from now? I hope there will be no more assignment statements representing updates to memory locations in a computer. I hope that we will no longer have to think like machines in order to program machines. I hope there'll be no sharp divide between programming databases and knowledge representation, no confusing assortment of human hostile syntax, and that all computer languages will be controlled natural languages, which are intelligible to people without any technical training in computer languages. It'll still be hard to write well, to write these knowledge representations, databases, and programs, but they should be easy to read. Well, that concludes my talk, and with luck, I'll be able to show you some of these programs. So we do have a few minutes, maybe. Well, I don't. Where shall I start? Let's look at the animation. Here's my living room. Initially, the light is off in the living room. Is that right? Initially, the light in the living room is off. In the kitchen, and we've got Dad. We've got Bob, who wants to switch the light on if it's off, and we've got Dad, who wants to switch the light off if it's on, and who can tell where the light is on. If the light is on somewhere, he'll go there. And we have the rules for initiating the light being on and initiating the light being off. And when a person goes to a place, that changes the person's location. So let's run this. Let's run this with the little bit of Prolog, which displays the animation. So we'll do that. So Dad is going to the bedroom, shut it off, going to the bathroom, shut it off, going to the living room, shut it off. Bob puts it back on. Dad shuts it off, switches it off. And because I've declared that time ends at time 12, that was it. But if I give it a little bit longer, you'll see it will just take that much longer. And of course, we can pause this anytime we want. So here we are, Dad and Bob consecutively switching the light on and off, and this could go on forever. So the model which LPS generates is an infinite model, and what we want to know is that the agent's goals can be satisfied, and this requires the notion of truth to be relative to a model rather than a proof theoretic notion which can only be determined finitely. So do I have Mark wanting to say something? let's look at another example. Here we have Bob and Fariba. Bob has got no money in his bank account. And Fariba, my collaborator, has 100 units of currency. And Fariba, having pity on me, transfers 10 units of currency to me from time 1 to 2. But whenever Fariba transfers money to me, and I have in my account an amount which is greater than 10, then I will transfer 10 units of currency back to her. So if she transfers, let's see, well, let's not go into the details. Here's a little bit of a prologue display, and let's see what that display looks like. So Bob and Fariba are transferring funds back and forth to one another. And Fariba, who started out wealthy, ends up being impoverished, and Bob ends up having the money that Fariba had to begin with. And that's because of the way the reactive rules. So you can see this is driven by reactive rules, driven by goals. And these are the goals that Bob and Fariba have as viewed by an external agent. They also make use of constraints to make sure that we don't transfer, that the same person does not transfer more than one amount at the same time. I might mention that the implementation maximizes concurrency, so that all actions that can be performed at the same time are performed at the same time, provided they do not violate constraints.
Thank you, Bob. I didn't see any questions raised hands in the Zoom, but I did see 2 thumbs up, which is a good sign.
Okay, well, I also see I have, if I'm not mistaken, 30 seconds left, and I think I'll use that to finish early. So thank you very much.
Thank you. Okay, with that, I give my reins back to Peter. And
Okay, thank you. I actually had a question, but I don't see how to raise hands on this thing. So
yeah, right now I see that some people raised hands and then lowered them back.
So
okay,
can I ask a question then? Since,
Yeah,
well,
sure. Yeah.
I have a conflict of interest here, but my question is that this is in synchronous programming time, you have a sequence of time instants, and within each instant you can do an infinite amount of deduction, which takes 0 time, and whatever you deduce can affect what happens in the next time instant. So this is synchronous programming. This looks very similar somehow to what you're doing. You know, like Esther Alger-Berry and even Vijay Saraswat worked on that. So you have each time instant, you can do arbitrary amounts of deduction, but it's no time, it's timeless. Yeah. But whatever you determine then can what happens in the next time instant.
Yeah, that's exactly, that's the way that's what we have, yeah.
Okay, so that's interesting. That's
well, I think the thing is that everybody's doing it or something related to it. I mean, so you mentioned other related work. I mean, there's so much more abstract state.
This is a very old thing, huh? This is from the 80s, but it actually, and Vijay worked on this in the 90s. So he based it on concurrent constraints, of course. But this is, it looks like there's a lot of correspondence, right? I mean, it's a very powerful way of modeling time. I mean, thinking in terms of logic is much more powerful than assigning variables, of course. Huh?
Yeah, down with variables. But basically, variables are really very simple kinds of facts oriented towards talking about the memory of a machine.
Yeah.
Oh, right.
Yeah, that was my only thing. So maybe we go to the next